Okay, everyone, welcome back to our Calculus 3 class notes. We are now on page 98, and we are in section 15.5, where we're first learning about triple integrals. And so what we want to find right now is the volume. In this example 88, find the volume of the region D enclosed by the surfaces z equals x squared plus y squared and z equals 8 minus x squared minus y squared. Hopefully these are simple enough surfaces that you could draw. This is just a concave up paraboloid, right? So this is the bottom surface here, z equals x squared plus y squared. And then z equals 8 minus x squared minus y squared is the concave down paraboloid. So it starts up here at z equals 8 and it starts flowing down. Okay, so this is the domain. We're trying to find the volume of this domain. Sort of looks like an egg. Okay. So we want to integrate. We want to determine the limits of integration as follows. So the triple integral dv will find the volume. So we want to do dz dy dx. The reason we want to do dz dy dx because we got to think about where these two guys intersect, and the region that we're going to integrate over the xy plane is this intersection. That's the shadow down on the xy plane. So this is our region R. So this region will be dy dx. We'll use dy dx for this. So that should be our outside 2. And then z will go from the lower surface, z equals x squared plus y squared, up to the upper surface, z equals 8 minus x squared minus y squared. So when I look at the intersection of these two surfaces here, I set them equal to each other and I see, oh, their intersection is a circle with a radius of 2. So there it is, there, and if it plops down, I see the shadow on the xy plane. That gives me how I can find dy dx. So I'm going to do, as x goes from minus 2 to 2, y will go from the lower half of the circle, which is minus the square root of 4 minus x squared, to the upper half of the circle, which is positive square root of 4 minus x squared. So I kind of explained all that in steps 2 and 3 here. So first to find the z limits of integration, then I found the y limits of integration, and then I want to find the x limits of integration. Okay, so I usually think of, when I'm finding the area of the region, I think of step 3 and 4 as kind of being one thing, and I actually almost think of step 4 first. This is really how your author said to think of it, and that's probably the most, if you're looking for a rigorous step-by-step method, this is the way to go. But I like to say that the outside integral needs to be constants. So dx is the outside, goes with the very first integral. So x has to go from one constant to another. That's why I know it's from minus 2 to 2 to cover this region. As x is going from minus 2 to 2, y is going from the square root of minus the square root of 4 minus x squared up to the positive square root of 4 minus x squared. And then the inside integral is where z is ranging. So z is ranging from the lower surface to the upper surface. Okay, so this is what I have. Now, I really can think of this as a very symmetrical thing here. So if I just did it over one quadrant here in the xy plane and then multiply that by 4, because I'm going to find 1/4 of the volume that's above that region if I just look at the positive, where x is positive, y is positive. So by symmetry it's 4. Then if I go from 0 to 2 for x and 0 to the square root of 4 minus x squared for y, and then z still goes from x squared plus y squared to 8 minus x squared minus y squared. Multiply that times 4, I'll get the same answer. It just makes some of my calculations there later simpler. So integrating 1 dz just gives me z. Evaluate that using the fundamental theorem of calculus. This is what I get after I simplify. Then I want to integrate with respect to y, so I'm going to get 8y minus 2x squared y minus 2/3 y cubed. Right here. Right. So what I do, I factor it out of 2. Actually, I factored out 2 first up here. I'm sorry, I factored out 2 here. So I pulled out a 2. So that leaves me 4 minus x squared minus y squared. Then I integrate it. So 4y minus x squared y minus y cubed over 3. Evaluate from 0 to the square root of 4 minus x squared, plugging those in for y. Do a little bit of simplification. I see that there's a square root of 4 minus x squared here, and there is another square root here. So what do I have? If I factor the square root of 4 minus x squared out of these two, I get 4 minus x squared times the square root of 4 minus x squared, right? And then I get 4 minus x squared to 3 halves over 3 still, okay? So then notice that this is to the 1 and this is to the 1/2, so these combine as well. So I end up with, this is 1 minus 1/3 times the square root of 4 minus x squared to, I'm sorry, 4 minus x squared to 3/2 power. So that's 2/3. That's where the 2/3 came from. So this is what I need to integrate. Okay, so the problem here is that this integration now I'm going to need a trig substitution. Anything else I try would not work. Trig substitution is sort of our last resort with our integration methods, but I need to use that here. So this is of the form a squared minus x squared. So I am going to need to let x equal a sine theta to continue this problem. Okay, and I'll finish the problem in the next video.